Hello. Yeah, this is Kishan Shenoi, and this is one of the talks of the WSTS 2023 tutorial session. You notice this is a virtual session, and the whole intent of the tutorial, which is comprised of several talks, is to get you up to speed, to act as a refresher, maybe answer some questions, and prepare you to better understand and appreciate the different talks which will be given in the actual workshop itself in Vancouver. So this is the first talk. It'll be on the fundamentals of timing and synchronization, and I'll talk about basic principles, the fundamental need for synchronization, and transfer methods for transferring timing information from point A to point B. So a clock is a frequency device actually. It's based on physics and it provides ticks at precise intervals. And the interval is sometimes referred to as a period. The frequency of the clock is the reciprocal of the period. So then we can think of clocks as electronic systems that count ticks to get time interval. So from a given starting point, a time clock provides elapsed time by counting the number of clock ticks from the start. The granularity of time you can present is related to the tick period, and we can use PLLs to reduce the tick interval or increase the tick rate, and or use dividers to increase the tick interval by reducing the rate. So consequently, we can think of time as a combination of the event, that's the instant that we're looking at the time value, and the time value is essentially the elapsed time from an agreed upon starting point. So when we have two clocks, we can consider whether they are quote unquote equal, and notion of equality or alignment or synchronization of two time clocks implies that they are equal in frequency, phase, and time. So what do we mean by alignment in frequency? I've done this by taking two clocks. At the base level, you have the tick generation. If the tick generation is the same rate, they are aligned in frequency, and this is known as synchronization. They are phase aligned if the edges align up. Now, looking at each edge may be tedious, so we may count down. So in this example, I've assumed that the basic tick generation is 10 megahertz, and we have a 10 million counter. So we get a counter rollover after every roughly 1 second. So if the seconds rollover is coincident, then we say they are phase aligned. Now, every time this rolls over, we can have another counter for seconds. Now, let's assume that both the seconds counters start at 0. Then, as long as they are time aligned, we'll see an equal number of seconds. We can make it a little more fancy and look at time alignment in terms of local time, because then we have to take into account where we are in the world, what time zone, etc. So basically, the difference between the time values of the two clocks is also referred to as the time error. So a clock is a frequency device providing ticks. Electronic systems count ticks for time interval, and time is essentially a combination of event, which is the instant we are looking at, and a time, elapsed time, shall we say, from the chosen starting point. The chance of two clocks being perfectly aligned is very small. So we have developed a bunch of metrics to quantify misalignment. At the very basic level is the notion of time error. And the way we define time error is, if you look at the edges that we are looking at, either the ticks or maybe the 1 second rollover point we used in the previous example, we look at the time difference between corresponding edges, and that is the time error. Time interval error is an extension, and that is when we are looking at two clocks which are measuring the duration of an interval of interest. So the error in the, or the difference in the duration measurement is the time interval error. The two metrics that we'll talk about, and there's another section on clock metrics coming up, but the two major metrics we look at are MTI and TDEV. MTI is a measure of maximum error, whereas TDEV, or time deviation, is more a measure of stability in terms of like a standard deviation. When we deal with clocks, there's two important properties. One we call accuracy and the other stability. They sound similar, but they are actually quite different. When you think about stability, it's a measure of consistency, and accuracy is how close you are to the truth. So you can have something which is stable but not accurate, like the bullseye pattern on the left-hand side, or you can have something which is very stable and very accurate, and that implies that you are hitting the bullseye with a tight grouping, whereas stable is just a tight grouping. When we deal with oscillators in particular, we are very worried about stability and not so much about accuracy, because very often we have a reference available with which we can control the oscillator. And as long as it's stable, we can do a good job of calibration. The fundamental need for synchronization, I'll look at three different areas: signal processing, events, and buffer handling. Signal processing requires good synchronization. Why do I say that? When we process signals, it's usually in the form of digital signal processing, where we've taken samples. So there's a notion of, if the sample is taken at the wrong instant of time, that introduces an error. And since the sampling is governed by the clock, the synchronization error of the clock can be translated into something like a noise. So think about epsilon of t is the difference between the true value x of t and this sample that we've actually taken, which was taken at the wrong time. And this delta is like the time error. So synchronization error we can actually quantify in terms of signal to noise ratio. That's what I show here. The noise is just the difference between what you expect and the delayed version of it, the delay being a result of sync. And we see that the SNR drops dramatically as the time error increases. That's number one. And number two, it drops also with the bandwidth of the signal. So the wider the bandwidth, the more drastic is the drop. The important thing to take away from this slide is that if you are going to do any kind of signal processing, and we do, especially in wireless, you need good synchronization. Other cases where synchronization is important, think of timestamping events, especially if you want to see which event occurred, before another, and especially if these events are in geographically disparate locations. The way to do it would be to timestamp the events with clocks which are synchronized to a common reference. There are many examples of it, like distributed databases, stock trades, sensor fusion, etc. Another good example for synchronized clock applications is in verification and validation. This is best exemplified in the stock market, where timestamps are used to chronologically order trading activities, even across continents. Then in traditional telecom, or so-called TDM, where multiple data streams were merged together, they would have to have exactly the same rate, because otherwise you would not be able to interleave them. And if you did any buffer processing, these buffers would overflow or underflow. I'm going to talk next about the transfer methods. So this is how you deliver timing information from one point to another. So the basis, you need to do that in order to synchronize two clocks. Take the example of transmission of a bit stream. The source or transmitter clocks out the bits using a TX clock, which is its clock. The waveform goes to the receiver, where in order to extract the information, he has to do a clock recovery operation so that he can identify what is the bit interval and what is a good place within the bit interval to take a sample to get a decision on whether it's a digital 1 or a digital 0. That is the clock data recovery portion of it. But clock recovery, when it's done correctly, the time period of the RX clock at the receiver would be basically the same as the time period of the transmit clock. The transfer of time is a little more interesting, to say the least. If the master sends out an event and tells with a timestamp T1, and that event reaches the slave, and the slave looks at his clock and says the time according to my clock is T2, then his first guess as to how wrong his clock is T2 minus T1. But that does not take into account any transmission delay of that event or that packet or that message going from master to slave. So there has to be a way of establishing what is this time delay. In order to do that, we use a two-way method. That is, the slave sends a packet towards the master. He records what time he sent it, which is T3, and the master gets the packet and sees what time it arrived, and that is T4. So we have 4 timestamps, T1, T2, T3, T4, which are delivered to the slave. The slave makes an assumption that the transmission delay in the two directions is the same. And consequently, he can establish what is the round-trip delay. And assuming that that symmetry I just mentioned, the one-way delay is 1/2 the round-trip delay. Based on that, he can establish, and that's the equation 3, the offset from master of the slave, or OFM. There's the formula given. It's 1/2 of T4 plus T1 minus T3 plus T2. So he knows how wrong his clock is, and he can adjust it. Now, strictly speaking, that this is not done just once. It's done continually, so that the slave clock maintains like an algorithm or a servo to keep track and keep his alignment with the master intact over time. So that is synchronization, actually. So basically, this brings me to the end. The topics we talked about were some basic principles of time and frequency, the notion of alignment. We talked about the fundamental need for synchronization. For example, coordinated signal processing requires phase alignment, and we'll see that on many occasions when we talk about wireless transmission in 5G, 4G, 3G, whatever. Timestamping events, especially in geographically separated locations, requires time alignment, of course, and you need that in order to decide events and ordering of events. And in some applications like distributed databases, time alignment is extremely useful. When we do buffered transmission, where the data source is written into a buffer and the data sync reads from the same buffer, the read and write clocks require frequency alignment, or the buffer would overflow or underflow. The third item we talked about was transfer methods. We talked about 2 methods. One was one-way, and that is really good for transferring bit period, which is essentially transferring frequency. And the other was to do not just transfer bits or bit time, but also measure the round-trip delay, which allows the slave to align its actual time clock with the master's time clock. Well, that brings me to the end of my presentation. Thank you very much for listening. And if you have any questions, comments, or suggestions, please do ask me, and you can reach me by email. It's given there. And I hope to see you in Vancouver. Thank you.